Okay, let's get going. This is 5065, QMSS class, Bayesian Statistics for the Social Sciences. I am Ben Goodrich, and today we're going to be just going through some introductory material, somewhat based on the readings for today and the video on the syllabus. And I think the main goal for today, also next time, but especially today, is to get a feel for what this class is about and put you in as good a position as we can as to whether you want to take it. I think a lot of people try to decide what classes they want to take before they invest time in the syllabus and the books and whatnot, but that's really backwards. You need to dive into the syllabus in order to understand if this is something that you want to do for the rest of the semester. So, I mean, every week it's important to do the reading, but particularly the first few, so you get a sense as to what the rest of this class is going to be like. So, first thing I want to start with is this chart plot from an article that was published, it's now been a few years, by Lynch and Bartlett in the Annual Review of Sociology, documenting the prevalence of articles that use Bayesian methods over time. And so starting with this purple line here for applied statistics, you can see in the 1980s, this plot goes back to 1978, but even if you went back to 1778, it would say about the same thing, a handful of articles per year using Bayesian statistics. Starting in 1990, it jumped up, and since then has been increasing at a fairly rapid pace. And I think if you extended this to 2023 or so, it would show about the same trend. So the first question we need to ask ourselves, and it's actually a pretty important question, why in 1990 did the use of Bayesian methods take off in applied statistics? So who has a theory as to why that might be the case?
Is it related to computing power and accessibility?
Computing power, yes. Computing has a lot to do with it. But computing power increases at a very smooth, predictable rate for the most part. Why do we think in 1990 there was almost a vertical discontinuity in it? Did you have a thought?
.com crash?
.com crash. No. The .com crash was a bit later in the 1990s, but also the companies crashing the .coms, I think, had not really heard about Bayesian inference that much at the time. This is published articles, so very much the academic prevalence of the use of Bayesian statistics. Who else has an idea as to what might be responsible for the tremendous increase in Bayesian articles and applied statistics starting in 1990? Yes?
Is it related to bootstrap or simulation techniques?
Simulation, yes. Bootstrap, not so much, but simulation, yes. In particular, in 1990, there was an article published in the Journal of American Statistical Association that showed how Bayesian estimation could take place using computer simulations. And that made Bayesian inference a lot more general than it had been in the previous couple centuries, where in order to come up with a Bayesian estimation, you would have to solve an integral. And many integrals just cannot be done in an explicit form. And so although Bayesian inference was very general, in practice before 1990, there were only a few very special cases in which it could be conducted, corresponding to the very few special cases where the necessary integral could be worked out with like a pin. But starting in 1990, like I said, this article that was published said you don't have to do the integral. You can do computer simulations to give you the Bayesian estimate. And so that is in part a question about or a story about technology. Starting in about 1990, maybe a handful of the young professors in a university might have their own computer in their office. Nowadays, you have a computer in your pocket that is much more powerful than the ones they were using in 1990. But it helped that the technology was starting to come from like a processor perspective, being able to do this reason, not fast, but faster, have more memory, etc. But it is mostly a story about software, because once this article was published in the Journal of American Statistical Association, then software started to be able to implement that algorithm and make Bayesian inference possible. And so when you sometimes hear people, like in the video, refer to modern Bayesian inference, they're talking about since 1990, as opposed to ancient Bayesian inference, which entailed or required solving an integral, which in most cases couldn't be done. And so, as compared to a lot of other things in statistics, modern Bayesian statistics is a millennial, like most of you. But the theory of it and the ideas for it, like I said, you could call it ancient Bayesian statistics, goes back to the 1700s and is actually older than everything. Right? But we could get into it a little bit more. Okay, so if that is an explanation that you're just going to have to sort of trust me on as to why the prevalence of Bayesian statistics has increased so much in applied statistics journals since 1990, what explains why there is a decidedly more muted increase in the use of Bayesian statistics in articles published in social science journals? So not applied statistics, but economics, political science, psychology, and sociology. Yes?
I think like their data methods are different, like there's a lot more like field work and they tend to be a little bit more like qualitative like on that side, so they might not really think about incorporating those methods.
Yeah, so certainly it's true that particularly with sociology and things like that, there's less quantitative articles total. There's more theory articles, more articles that use qualitative data, etc. I think they did the authors did this survey from journals that at least somewhat regularly publish quantitative articles. So you could maybe say, give an explanation as to why, the whole purple curve might be shifted down if there are fewer quantitative articles in sociology and whatnot. But it seems to not even really be the same trend. Like it increased a little bit, maybe starting after 1990, but honestly not that much at all, not with the same slope. So does anyone have any other theories as to why the increase in the use of Bayesian statistics in applied statistics journals hasn't been matched or even paralleled by social science journals?
Is it partly because for social sciences like economics, frequentist thinking is very prevalent in how they do research?
That is true, but it pushes back the question, why is frequentist reasoning so entrenched? I mean, certainly it was entrenched in applied statistics prior to 1990 as well, and things have changed a bit. But yeah, I think that's the start of the answer.
It may be due to the end of the Cold War, so more funding could be moved to the social science, I think.
It's certainly true that the budgeting and funding and things like that changed. And there is an interesting connection between the use of Bayesian inference and military stuff that was talked about a little bit in the video. So not that many people know this, but could argue it is the case that Britain unlost World War II because of a theorem, Bayes' theorem, which Alan Turing, among other people, applied to crack the encryption code used by the Nazis when they were communicating messages to their submarines, and the submarines had essentially surrounded England and made it difficult, if not impossible, for slow-moving boats with food to come across the Atlantic Ocean. And so England does not produce enough food for its whole population and has to import it. And if the food boats are getting sunk by submarines and the Allies didn't know where the submarines were, then you have a serious problem. But the encryption codes were not that sophisticated in the 1940s. Alan Turing was able to use Bayesian inference to crack them with the help of a lot of other people who were involved in that effort, and an extraordinary act of bravery by the part of two people who actually went onto a sinking boat to steal some data to bring back the feed to this. So, sounds like if it's true that England unlost World War II because of a theorem, that might be a theorem that you all should learn about, irrespective of whether you want to fight a world war. But it might have broader applicability. Unfortunately, Churchill, who basically only did one thing right his entire life, one of the things he got wrong was immediately after World War II, he made all the stuff about Bayesian inference and cracking the encryption and all that double super secret classified because they thought they were going to have to use it against the Soviet Union to drive them out of Eastern Europe. That didn't really happen. Nobody had enough guys left to fight another war. But anyway, the Turing and the other people weren't even allowed to discuss this because Churchill covered it under military secrecy law. And so that set back the dispersion of Bayesian stuff a good amount of time. But I digress. It has a little bit to do with military stuff, not that much to do with military stuff. Yes?
Maybe just the nature of the research questions asked in these topics just might not invoke Bayes' theorem, because at least from my perspective from economics, a lot of the questions that we dealt with relied on cross-sectional data, looked at one point in time rather than just something that happened over time or a dynamic process.
That is certainly a plausible theory. Maybe something about the nature of social science doesn't lend it, or social science research doesn't lend itself to Bayesian inference. And that, at least according to the graph, might make sense. But that would then raise the question, why does the quantitative methods in the social sciences program at Columbia University have a class, whole semester, devoted to a quantitative method that is not used very much in the social sciences? It seems like a rather disturbing question. If, in fact, something about the process of research in the social sciences does not lend itself to Bayes' theorem, and that's one of the things that I want to encourage you to have faith that that's not really the case. Social science is at least as amenable to Bayesian reasoning as any other science, chemistry or physics or whatever, if not more. And the reason why I would argue we don't see the same prevalence or same increase in the use of Bayesian statistics in the social sciences as compared to applied statistics has to do with the use of probability. So if you're a statistics grad student or even a statistics undergrad student, you're going to have required courses, at least one, if not more, in probability theory. And so you get, whether you like it or not, more comfortable with the idea of talking about probability distributions and the manipulations of probability. In contrast, in the social sciences, you have your required classes, but they don't really get into much detail about probability. Maybe they refer to it a little bit. But most classes, the quantitative methods classes in the social sciences, including those in QMSS, are very much focused on how to do something. There's decidedly less attention paid to, well, what are you doing? And very little, if any at all, particularly in introductory classes, as to why you're doing it. So the emphasis, like 90% of it, is on how to do something. A little bit maybe on what you're doing, but not so much why. And really, to get into the whys of it, you have to bring in probability theory backing it. And that's not something that social science programs historically have chosen to do very much. And so that's the main thing. That's the main thing that makes this class difficult. Starting next week, we're going to go deep into probability, even though that's something that maybe not that many of you have had a class that specifically focuses on. And so first we have to learn more about probability before we can really learn about the mechanics of Bayesian inference, before we can really learn, after we sort of said what and why, get more into the how of it and whatnot. So that's the main thing that I think makes this course difficult, and by the same reason, difficult and less prevalent in social sciences is you have to have kind of a minimum level of comfortability with probability, which is not something you really get at all at the undergraduate level in social sciences, and not nearly enough of at the graduate level as compared to what they would do in statistics or even in the data science master's program. All right. So we had one person mention economics, a couple people already maybe. Who all is the econ concentrated? Okay, 2. And you've already spoken, so I'll ask you. So among social sciences, which is the plot over here on the right, we have the number of Bayesian articles per 1,000 published by the journals. Why do we think, or why do we speculate that the prevalence of Bayesian articles is much more in economics, particularly starting after 1990, than all of the other social sciences put together? So why econ among the social sciences?
Could it be because within the social sciences, econ is probably one of the least qualitative data that we use.
Right. So certainly a lot of quantitative data in econ, and that may be part of it. Even though I would say Bayesian inference can be applied to any sort of data, quantitative, qualitative. Matt, you had a theory?
I assume because economics is also very like future oriented in that sense that like, you know, the probability is like a huge, you know, thing in terms of like, you know, trading is gonna look like, you know, I don't know, it's gonna look.
Yeah, so there might be a little bit more discussion of probability in econ courses, econometrics and whatnot. Nisha?
Yeah, I was gonna say like the volatility of like the markets, like kind of adding on to your point, like, you know, predicting like recessions and like growth and all of that. So I know like economics tends to focus a lot of that, like with markets and trade and all of that.
Right. So you'll see articles saying, you know, a bunch of economists, they predicted a 40% chance of a recession in 2024. So speaking in terms of probability already.
They also maybe game theory drives it too, because it relies a lot on what the person prior did, what your next move's gonna rely on, what the other person might do or what they have done.
Yeah, that's really what I was getting at with the econ thing. So in game theory classes, which is pretty much going to be required in any graduate econ program, whether master's or PhD, not only probability, but Bayesian probability is at the forefront of it when analyzing the decisions that the people in the games make, whether we're talking about Prisoner's Dilemma or monopolistic competition, all these sorts of different games. Game is kind of a broad term, but strategic interactions. It's very common in economics to assume the firms or the people, whoever's in the game, the players, are using Bayesian type reasoning as best they can to decide what to do. And so you're going to get more exposure from that way in terms of people thinking about probability and Bayesian updating and things like that. So even outside of game theory, if we're just talking about macroeconometrics, things like that, the use of Bayesian inference in terms of relative terms, relative to the rest of social sciences, high, because those people got some incidentary exposure when they took their game theory classes in economics. So it's the same probability, but it's being used in sort of a theoretical way in game theory, maybe more of a mathematical way. Whereas what we're going to be doing this semester is going to be geared toward empirical applications, estimating the parameters that might appear in this or that theory, whether it's a game theoretical model or not. And so I think that to me is probably the best explanation for why in relative terms Bayesian stuff much more prevalent in econ than in the rest of social sciences. So turning to psychology, did you have an additional point about the econ? No? Okay. Psychology seems to be the only place in social sciences where the use of Bayesian inference is increasing at a fairly rapid rate from nothing to almost nothing. Whereas even in economics, where it's still higher, it's not even clear that it's really increasing anymore. It looks kind of leveled off. But in psychology, much more so than political science or sociology, we do seem to be, at least as compared to what it was, increasing at a relatively rapid rate from an extraordinarily small base. And why might that be? Where's my psych ward? I know there's some people, yes.
I'm thinking maybe that whereas the other social sciences kind of come from like surveys or publicly available data. Psychology, like when it's a study with human participants, that's very like cost expensive, and you know there's a lot of like IRB protocols in place that kind of prohibit certain things. So being able to use Bayesian principles and kind of just any type of like resampling or anything to get more robust results without actually spending more money or crossing any like IRB lines.
Yeah, I think you know you've got IRB considerations in sociology and other things like that as well. But it's kind of always been the case. Uh, it's always been the case a little bit. But what about psychology has changed in, let's say, from like 2000 forward that might make Bayesian inference be more prevalent? Did you have a question or a theory, statement, anything? Words.
I don't know, I was just thinking, like in general, like, I mean, I have never studied psychology, but I
Neither have
like
I.
there is a lot of like research on like human behavior, and, like, you know, like, kind of like having like a way to like project human behavior in that sense, and like, I don't know, statistically trying to like predict something, which is obviously so hard, cause like there are so many like outside factors for that.
That's part of it. Did you have a thought?
I guess it's just trying to be more like a science, I would say.
So maybe there's a trend toward being more quantitative in psychology in the past 10, 15 years. So like I said, I've never studied psychology, but I've heard that it's in crisis. Anybody else hear about the crisis in psychology? Yes?
It probably is more across topic and psychology than associated with representation.
Yeah. So psychology, elements of it and collaboration of it has increased with the other social sciences, also neuroscience, where Bayesian stuff is done a little bit. But back to the crisis. What? Okay, so who knows the actual crisis in the crisis of psychology?
The replicability crisis in psychology.
Replicability crisis.
Actually, I mean, I don't know if this has anything to do with it, but it was an experimental economics article that came out in the early 2000s that talked about the pitfalls of psychology, how it compared to experimental economics, and how there were certain, I guess, practices in the lab that were inadequate. So I don't know if that maybe had some sort of influence, or maybe it was a byproduct of the replication crisis, but it was just kind of a thought.
Yeah, I think part of the stuff about the replication crisis in psychology is about research methods and increasing emphasis on making your data and code and stuff available, in which case there's people out there who might want to replicate or try to replicate the study and find that it can be done. But there's also an important element of that, which is the statistical methods being used. Do they exacerbate the crisis of this crisis in psychology? And I think an argument can be made for that, that the frequentist methods that have historically been used in psychology with the testing of null hypotheses and things like that as a way of assessing whether something could or could not be replicated might be actually part of the problem, and if so, open up an opportunity for alternative estimation and inferences that don't utilize null hypothesis testing to get more of an opportunity to be used in psychology. Now still, we're just talking about like 8 or so articles out of 1,000 as of 2017, so still not very much, but maybe more so than in the past. Anisha?
Yeah, I was gonna say also too, with a lot of the psychology studies, it's very longitudinal, so like trying to like keep in track of like, especially if you're looking at development and like adolescence and all of that, like making sure that like you're keeping track of like the progress and all of that, so that might also be like where you would need those methods too, and I know, I think even like political science is also a little bit much like that too, but I was thinking a big thing with psychology is like the longitudinal studies.
Did you have something you wanted to add with that?
Just in general, like most, like a lot of like established theories in psychology are oftentimes like, I don't know if it's not taken seriously in that sense, the correct thing, but like they lack show evidence, like.
There's definitely a generational division within the crisis in psychology. That a lot of it is the younger professors, the postdocs, the graduate students who are finding all kinds of articles written by the full professors and people who've been doing this for decades that they don't replicate, and that is part of the disagreement and the infighting, particularly among social psychology. And then, sociology and political science, honestly, never was very much. So circling back to the question, why does the quantitative methods in social science program have an entire semester class on a quantitative method that is not utilized very much in the social sciences, if it's not the case that the data somehow don't lend itself? If there was anything where you might say the data don't lend itself to Bayesian inference, you would be talking about these giant terabyte size data sets. But those are not so prevalent in social sciences, even although the sizes of data sets are getting bigger in some respect. Okay, so if it's used like a little bit in social sciences, if it's used more in econ than the rest of it, that raises some more questions. So how many of y'all took 50-15 in the fall, like data analysis in the social sciences with Greg or somebody else? Okay, that's most of you. All right, so who remembers what textbook you used for that class? Wooldridge. All right, very good. You passed the test. First day, managed to remember who wrote that textbook. So what edition of that textbook did you? 7th or 8th. Anyway, there have been a lot of editions of that textbook. And how many pages would you guess were in that textbook? Like this book?
Yeah.
800, 900, something like that. So we got like 7, 8 editions of Jeff Wooldridge's textbook, each of which are roughly 900 pages in length, not to mention hundreds of dollars in cost. So of those, let's call it 900 pages, on how many pages did the word Bayesian appear?
I know 0.
0. So that maybe gives a start of a theory as to why Bayesian stuff is not used in the social sciences. You have leading textbooks such as Wooldridge's, among others. I'm not really picking on Jeff Wooldridge here. But a lot of the other introductory textbooks that could have been used in other classes have you can have less mentioning of Bayesian than 0, but they have little to none discussion of that, despite the title of Jeff Wooldridge's book being Introduction to Econometrics, a Modern Approach. So you might think the modern approach would include all this post-1990 stuff. Okay, so maybe the reason why it's not used so much in social sciences is the introductory textbooks don't actually introduce Bayesian inference. And that's, I think, part of the story, but it pushes back the question, why do people like Jeff Wooldridge not mention Bayesian inference in an introduction to econometrics, the modern approach? So that's by choice. And again, I'm not really picking on Jeff Wooldridge, because I've heard would be a strong word, I've seen on like Twitter and whatnot, him give some explanation as to why he does not want to use Bayesian methods, but he doesn't put it in the textbook, despite there being 900 pages, 8 editions. I think a 9th edition is coming out in April, so can see if it includes some discussion of Bayesian inference, but I'm not holding my breath. I'm certainly not going to hold my breath until April, and I'm certainly not going to hold my breath that Jeff Wooldridge writes anything favorable about Bayesian estimation. Anyway, it's his book. Can write whatever you want in it, but the standards for textbooks are a little bit different than the standards for publishing an article. Like if you wrote an article anywhere in the social sciences and submitted it for publication, and nowhere in the article did you like acknowledge or respond to, there might be another group of scholars who say this whole thing is completely wrong. In an article, you can't just say, I'm not talking about this at all. You have to at least put a footnote to say like why it is you're dismissing a whole other chunk of articles. But in a textbook, you can kind of do whatever you want, and Wooldridge doesn't want you to learn Bayesian inference. So he doesn't talk about it in his $300 book.
Maybe he doesn't understand it.
He does. Well, maybe he doesn't, but he does. He understands probability very well. He understands the difference between Bayesian inference and frequentist inference, which is pushed in his book. And he's gone into some detail as to why he thinks what he thinks on Twitter. But it's not in the book, and so you might, or there's a lot of other people in the QMSS program who are not here, who took 50-15, read the majority or whatever of Wooldridge's book, and wouldn't come away from that saying, oh, well, maybe I should learn Bayesian. Because it's not even mentioned. Much less like, what are the differences? Much less, why would you prefer one to the other? And that is something that I find tremendously frustrating, is that in 2024, people who favor frequentist approach, people who favor supervised learning approach, stuff like that, okay, they favor what they favor, maybe they have reasons for it, but their preferred way of promoting their favored quantitative method is to not talk about alternative ways, like Bayesian. Whereas we're going to talk a lot about how Bayesian differs from others and why and things like that. This isn't a class about frequentist inference, but we have to refer to it a lot in order to explain how Bayesian differs fundamentally from it. And so, you know, in 2024, it's like I'm arguing against someone who's not even bothering to argue back. So, like, how do I need to improve my argument to convince the Jeff Wooldridges of the world of the virtues of Bayesian inference if they're not even gonna, like, he has unlimited number of pages the publisher will let him put in the textbook because he's made, you know, millions of dollars for his publisher, something that he could make it twice as long as he wanted. but he's not going to spend even a cent on Bayesian inference. But, you know, we're going to get into all of those things. Right? So, main point I don't want you to come away from this is, okay, Bayesian stuff is not used that much in the social sciences, therefore I don't need to be taking this class. That's consistent with the plots, but I think that's not the underlying reality. And also, the small usage rate of Bayesian stuff in social sciences is highly correlated with how well the person understands what they're doing. So over all the journals, like not very much, but people who are sort of quantitative methodologists within the social sciences, they tend to be the ones using Bayesian inference. And so it's very correlated with the amount, positively correlated with the amount of sophistication and training of the researcher. And that, I think, is the reason why QMSS is willing to have a whole class on it, because we want you to be on the leading edge, not like in the middle of social science research. Other questions, comments about what's going on here? So one of the textbooks we use is called Bayes' Rules. I think they have the exclamation mark in their title. I don't do the exclamation mark. But anyway, so it's online. It's on the syllabus. The link is there. They are not the only, but they're one of the few textbooks geared at the undergraduate level for Bayesian inference. And they wrote a paper about the prevalence or lack thereof in Bayesian courses at US universities and liberal arts colleges. So we're talking about the United States here. I don't know what is offered in every university in the world, but I'm pretty sure it's unlikely that you would be offered a Bayesian class outside of like English speaking universities. So anyway, let's just talk about the United States here. Of the 102 research universities, 45 of them had an undergraduate Bayesian class, so that's a little less than half. But of the liberal arts colleges, it's only 6 out of 50. So basically, in order to have a Bayesian course offered to you to take at the undergraduate level, you'd pretty much have to be doing your undergrad at a research university like Columbia. In the United States, as opposed to like a liberal arts college, or as opposed to you know, most other places in the world. But of those 45, most of the Bayesian courses being offered at the undergraduate level are in the stat department. So even if you went to undergraduate in the United States, if you weren't a stat major, or stat minor, stat concentrator, whatever it is, Columbia calls these things these days, and other universities, you might not even know that there was a Bayesian statistics course offered at your university if you didn't have some sort of affiliation with the stat department. And most people in the QMSS class are not statistics majors. They come from some sort of social science undergraduate program. And only 4 out of the 45 universities require the Bayesian course for the major. So even if you happen to be a statistics major at most of those universities, you could have fulfilled the requirements for a major without taking the Bayesian course. And even if you wanted to, or even if you were one of the 4 places that require the Bayesian course, among these 45, the modal number of prerequisite classes that the Bayesian course has is 6. Meaning that you would need to start planning to take the Bayesian undergraduate course probably when you're a sophomore or something like that in order to be able to do it by the time you're a senior. So one implication of that is basically now you're taking a graduate class without the benefit of previously taking an undergraduate class that may have introduced this at a more elementary level, and you, for the most part, haven't got the prerequisites that an undergraduate class would require. Now, 6 prerequisites might be a little bit extreme, but we can't really have prereqs in a master's program, particularly QMSS, which is ostensibly a 1-year master's program. We can't really say, oh, well, if you haven't taken these 6 classes, then you can't enroll in 5065 because you didn't really have the opportunity to take those 6 classes or whatever. Moreover, like if there was one class that you should have really taken, then like QMSS would probably give you a heads up, like, oh, you should take this in the fall if you want to take the Bayesian thing in the spring. But it's not like it's one class, it's parts of 6 classes. And so there's no way we can do that in terms of the schedule. Now that doesn't mean this class is impossible. Every year, most of the students that stay in it do quite well. But it does mean that you may encounter something where your background on it is a little bit shaky to not existent, which might mean you're gonna have to invest more time, studying that or learning how to do that piece of it in order to be able to proceed smoothly. So if you're a good student and if you have time, you can. But this is certainly the most time-intensive class that QMSS offers. So it's really a class about how quantitative methods should be used in the social sciences, although almost everything that we say is going to be applicable to science more generally, and even more generally to quantitative research, even if it's not, academic research. And Don Barry, who's like a pharma guy, had a quote which I really like, which says, Bayesian statistics is difficult in the sense that thinking is difficult. Underscores one of the main points that I want to make, that this class is really a class about how to think. Or as the authors of the Bayes Rule textbook pointed out in their first couple pages, it's a study about how and when to change your mind. And you might say, well, I change my mind, every day a whole bunch of times about things. I don't need a class to tell me how to do that. Well, you might need a class, and you probably do need a class, in order to learn how to change your mind well. There is, approximately one theory as to how to go about doing that, and that is to use Bayes' rule. So 5065, it's essentially a full semester of probability, although we're going to be doing that in less than a full semester, at the master's level. So entirely comparable to like introductory probability that you might see in the stat department, even though the stat department wouldn't let you into that class because they have hundreds of their own master students. But it's not just probability. It's a substantial part of theory and methodology that, ironically speaking, was not covered at all in the required course in theory and methodology that QMSS students are required to take their first semester. So it's not just Jeff Waldridge. Nobody in the theory and methodology class mentioned Bayesian inference either, or why you might want to learn more about it, when you want to use it, when not to use it. That seems like that would be kind of germane topics for a theory and methodology class, like a theoretical discussion as to which methodology should be used in the social sciences. Nevertheless, does not appear anywhere in a required class, and so we're going to fill in that gap Canyon. In the theoretical considerative methodology, learning new R packages that utilize stan to do 1 and 2. So, like I said, this is a story about software. But starting in 2011, although I don't know where 2011 appears on this, at Columbia, a bunch of researchers, myself included, but not exclusively me or even primarily me, a bunch of researchers associated with Andrew Gelman started writing new software for Bayesian inference starting in 2011 that utilized a new algorithm that was sort of second generation as compared to the algorithm that were used in 1990. That was the idea of a postdoc, Matt Hoffman, who came to Columbia in 2010. So, and that has led to, further increase in the rate of usage and stuff, less so in the social sciences, but somebody's using it a lot. It's downloaded many times every day, stuff like that. So we're going to be learning some new R packages. So that already sounds like, triple the amount of a normal QMSS class, but that's not even all of it, because fourth thing that's combined within all that is unlearning a lot of the things that you ostensibly learned before. But like I said, what you learned before was a lot focused on how, not so much what, and very little to none about why. And so you might have a whole lot of misconceptions in the what, why area that need to be addressed. And so a lot of what we talk about in this class can come into conflict with what you've learned in other classes, whether that's at Columbia or elsewhere. So I mentioned Stan, and when I mention Stan, I have to mention this other thing. So I work at Columbia. Columbia has received millions of research grants to develop Stan, and that makes them a bit uptight about the fact that I am 50%, along with a former QMSS student, of LLC, which uses Stan, and according to Columbia University policy, if any of several things, all of which hold, have to disclose the appearance of a conflict of interest. Don't really need to do anything as a result of that, except say it, which I have. And since I'm saying things, I might as well point out that Stan appeared prominently for 20 seconds of an episode of Billions, which you may be fans of. I think Billions ended. But anyway.
You ever done Math Meetup?
Is that what this is?
Yeah, it's a chance for like-minded users of open source programming language R and data analysis tools like Python, Julia, C++, and Stan to get together and exchange ideas.
It sounds stimulating.
It is.
It is. But anyway, if it's good enough for the showrunners of Billions, it's good enough for anybody. Let's leave it that way.
The only problem is that character is very unlikable. Going with the glasses.
Yeah, but it's not. It's a fictional story based on reality. So we're going to use R. If you've not used R before, that's going to be like a fifth thing. That may be the straw that breaks the camel's back. So if you haven't used R and you haven't used another scripting language, Python, something like that, is going to be very difficult because we're not going to spend time teaching the basics of R, since most QMSS students would have at least some exposure to R their first semester, which we're going to assume as a baseline. We have some non-QMSS students here, but that just sort of give you an idea of what sort of level of R we're talking about. The homeworks are going to be done using the Quarto markdown language. If you haven't done that before, that is okay. We'll demonstrate how to do it, but it's just like a way of synthesizing R code with English explanation, and it makes the plots all in one. It's a successor of R markdown, if you've heard about that before. So anyway, that's just like a formatting thing. If you know how to code in R, you can easily learn the format for the homework. But anyway, Stan is another programming language. We're not actually going to learn the Stan programming language directly. It can be accessed from a variety of other things besides R, but especially including Python, that you might prefer to use down the line. But it's very difficult to run a class where you're talking about multiple languages like Python and R at the same time, or like alternating. So we're just going to do R. But once you've learned the stuff that you need to learn in the class, you can use Python you can use Stan from Python or just about anything else after the course is finished. So, like I said, we're gonna use R a little bit, and if you know enough R to read this function, then you're probably gonna be all right. So this function refers to the Collatz conjecture, which has been referred to as the simplest impossible problem. And this function says if you start with a positive integer and repeatedly do the following things. So if it's an even number, divide it by 2. If it's an odd number, multiply it by 3 and add 1. And so the Collatz conjecture is that this process will eventually result in x being 1. For any positive integer. And so this is known as the Collatz conjecture, among other things, because neither Collatz nor anybody else knows whether it's true or not. In fact, like someone will give you like $1 million if you could prove or disprove the Collatz conjecture. And this utilizes a method of thinking that's common in mathematics and some forms of philosophy and whatnot. So if you could come up or find any positive integer where this function either goes off to infinity or goes in a cycle of some numbers, not including 1, and just stays in that cycle forever. If there's one integer, positive integer, that is inconsistent with the Collatz conjecture, the entire thing is completely wrong. One counterexample is sufficient to disprove conjectures such as the Collatz conjecture. Now, people have verified that a function like this terminates for every integer up to like 2 to the 60th or something like that. And you might say, well, if it's true or it holds for every positive integer, 1, 2, 3, up to 2 to the 60, like it's probably true for all the integers. But we don't actually know that. No one does. And so different people have speculated different things about whether this is true or not. But it has not been proven or disproven. But it could be disproven with a single counterexample. And like I said, this is a way of thinking very common in math and logic and some forms of philosophy and things like that. It is an exceedingly stupid way to think about social sciences, anything in the social sciences. Because for everything in the social sciences, there is a counterexample. There's a counterexample to a counterexample in the social sciences. There's nothing that we could insist on in the social sciences at the standard of, oh, if you find one person who is like inconsistent with the theory, then the whole theory is wrong. Because there's that one guy who's just inconsistent with everything. It's actually more than one guy. And so that is not a standard that we can or should or even entertain using in the social sciences. But, like I said, it does overlap with a lot of what goes on in philosophy in terms of classes on logic, which mostly go back to Aristotle. So this is sometimes called Aristotelian logic, or Boolean logic, or propositional logic. All these titles you can click on once you get the notes, and it'll take you to Wikipedia if you want more information about it. But Aristotle apparently said, albeit in Greek, which I don't understand, so I'll just give you the English version. 1, every human is an animal. It's known as the major premise. 2, Socrates is a human being. That's known as the minor premise. And if you put the major premise and the minor premise together, you come up with the conclusion, Socrates is an animal. And if you put yourself in the sandals of Alexander the Great, most famous student of Aristotle, and Aristotle dropped this knowledge bomb on you, you might say, well, this is almost a tautology as opposed to anything profound. Moreover, there's no one who really empirically disputed the fact that Socrates was an animal. Of course, he was dead by that time. Committed suicide rather than face charges of corrupting the youth with his teaching. But anyway, you might not be particularly impressed by this reasoning, although it has fascinated scholars of logic for millennia since then. But there are, I would say, 0 interesting applications of this form of deductive logic in the social sciences, because social science research by its nature tends to be more on the inductive side of things. But the closest thing I could come up with, not that I am advocating it, is a part of the political science research known as democratic peace theory, where the argument is almost in the same structure. 1, major premise, democratic countries won't fight a war against another democratic country. 2, minor premise, take any 2 democratic countries like Australia and Canada. 3, conclusion, Australia will not fight Canada in a war. Now, it's, I think, true that Australia has not fought Canada in a war. But you might say, well, there could be other reasons besides the fact that they're both democratic countries as to why they have not yet fought a war against each other. 1, they have like 150 people combined in population, so they don't need to be wasting any of them killing each other. 2, they're pretty much on opposite ends of the globe with hundreds of thousands of miles of ocean in between them. So what would they have to fight about anyway? But this is about as close as I can point to as something in the social sciences that mirrors the structure of Aristotle's famous introduction of propositional logic. But what most of social science goes something like this. As an example, incumbents in the United States with much more disapproval than approval tend to lose their re-election campaigns. So that's kind of like a major premise. But it's not like a 100% true major premise. It's just a tendency. Certainly there are counterexamples to this major premise. But two, let's say minor premise, Joe Biden has an approval rating somewhat below 40% at the moment. So that might lead you to the conclusion Biden will probably lose the election in 2024. But there's a lot of caveats to that. One, neither 1 nor 3 is like guaranteed absolutely true. The whole thing kind of seems plausible to some degree, to the extent that you accept both 1 and 2. But, 1 is kind of a weaker statement than a universal thing. It's not like every human being is an animal. That's like 100% true. Incumbents with much more disapproval than approval, they don't always lose, but they tend to lose. And, the approval of Joe Biden is somewhat below 40%. Well, how much below 40%? That makes a difference. As to how much stock you put in 3, Biden will probably lose, not guaranteed to lose. But this is a somewhat plausible sounding argument, but it depends on to the extent to which you believe 1 and 2 is going to influence, or should influence, how much stock you put in 3. You had a...
I don't know if it's a dumb question, but
No.
Bayesian statistics, I read a lot about like how it compares in comparison to other statistics methods uses like fewer like data in that sense too, right? To make or needs fewer to
Yeah, I've read many things along those lines. It's kind of a bit much to get into the first day. I would say it allows you to bring in other, or the implications of other data that might go beyond the data that you have right now in your hand. So you can bring in your past experience and things like that in terms of drawing conclusions about a new or somewhat new area in political science. On the other hand, like I alluded to a minute ago, actually going through the computation with the simulation and the stuff, the algorithms that I talked about or mentioned in 1990, and then the ones that we started doing here at Columbia in 2011, those have some limitations when you start talking about Facebook, Google size data sets in terms of the ability to do that computation within a reasonable amount of time. Now, for census-style data sets or anything less than that, the stuff that we're going to talk about this semester is fairly tractable. Mathematically speaking, it could be used on like terabytes of data. It would just take a very long time. But anyway, Bayesianism is a school of thought. It uses probability to describe your degree of belief and quantify your uncertainty about those beliefs that a proposition such as 3 is true. So I've sort of said it informally here, Biden will probably lose, but like how probably? You get almost guaranteed to lose, or more likely to lose than not, or anywhere in between. Or you might say, well, there's some other things, say his opponent is on trial for 91 different criminal charges that might make this one be, aberrant compared to the trend. So there's other things not being talked about here that might influence your thinking such that you think Biden is more likely to win than to lose. But anyway, Bayesian is a school of thought, a way of thinking, a way of updating your beliefs about the degree to which you think something is true, and to quantify your uncertainty about it, as opposed to this stuff from logic, which unfortunately gets picked up with frequentist thinking, that things are just true or false. Maybe we don't know which, but everything is true or false. Whereas with Bayesian thing, it's sort of upfront about, well, there's a lot of things that are shades of gray. More than 50. But anyway. And so, I lost my plot. Hold on. Gotta sign in again. And so, in the realm of politics, I'll see this in a second. Back to my plot here. Nowadays, we have futures markets. So, Predicted, among other websites, has this, website or whatever, where you can pay, you can pay some amount of money, and if Biden ends up winning the presidency in the November election, you get $1. Or you can bet it the other way. You can pay some amount of money, and if Trump or whoever the Republican nominee ends up being, if they win, then you get $1. And so you can see the price for these futures contracts evolving over time. Currently, the price for Biden is 41 cents. So if you buy the ticket or whatever and Biden wins, you get $1. But you have to pay 41 cents to do it. So kind of the Bayesian way of looking at this is, why would you pay 41 cents for something that pays you $1 if Biden wins, if your degree of belief, your probability that you think of Biden to win is less than 0.41? Why would you buy this thing? Or conversely, why would you buy a Trump ticket if you thought his probability of winning was less than 0.47 or whatever it is today? And so these futures markets, and we have them not just for president, but for a lot of other things, interest rates and all kinds of things, sort of imply a market-based probability with their price for these future events that no one is certain about. But using the futures markets to sort of express the market's degree of belief as to how much Trump or Biden, there's a small percent for Nikki Haley that I didn't even put on here, whatever, are going to win the election. And these change over time. So like last November, the markets were having a price for Biden that was much higher, or, in relative terms, than for Trump. But then, they started to cross, and then for a while they were pretty similar. And then in the past couple of days, not entirely sure why, other than someone bought a whole bunch of Trump tickets and that drove up the price on the Trump contract, whatever. But anyway, so you can imagine markets responding to events that update their beliefs as to who is more or less likely to win these things. That's provided by futures markets, but futures markets are not required to follow Bayes' rule. And so we want to learn kind of the way in which someone should update their current beliefs about some uncertain thing, whether it's uncertain because it's in the future or uncertain because it's like microscopic and you can't see it, or because it involves some latent parameter in your theory, like political ideology or something like that we can't exactly measure perfectly. Any sorts of things you can be uncertain about, in which case Bayes' rule is applicable, telling you how you would update your beliefs about the probability of these things as new information, aka data, comes in. And so that is what makes it sort of, I could say, fundamental for science. If you subscribe to the proposition that science needs a belief management system to update its beliefs about the state of science as new data, whether it's experiments, observational study, anything, comes in. So like I said, Bayesians use probability to describe their uncertainty about uncertain events, and there's many sources of uncertainty. You can have uncertainty about parameters in models. So let's say you have a regression, something like that, you have a regression coefficient, maybe an intercept. You can be uncertain, you should be uncertain, about exactly what numbers those coefficient intercept are. But you can also be uncertain as to which model is the best one to be using to describe some situation. So even in the context of regression, some people say you should use these predictors, other people say you should use these other predictors. How could we determine, or how could we make some sort of statement as, well, there's an 80% chance that this model is better than another model. So you can have uncertainty as to which model is the most appropriate to be using. You can have uncertainty as to what to do with the model output. So let's say you somehow decide one model is better than the other. Let's say you somehow obtain estimates of the parameters in the model. Now what do? So we talked at the beginning, predicting financial markets and things like that. So let's say you estimate all this stuff. How would you use it to form predictions about the future of the stock market and to quantify your uncertainty about those? Because we can't be certain about those things either. Fourth one is a little bit different. You can have uncertainty about whether your software works as intended. And that is something that we tend to take for granted. But the McElreath reading on the syllabus today provides a lot of reasons for caution as to maybe why you shouldn't take it for granted. Because the software that we tend to take for granted was intended to use, or was developed a long time ago for the sorts of situations that researchers were facing at that time in the past. But when you're doing scientific research, or even research outside of academia, you tend to be on the bleeding edge of knowledge. You're trying to find out something new and be, in a manner of speaking, not necessarily contrarian, but fundamentally different from what the state of scientific knowledge was yesterday. And so you're applying methods that were developed a long time ago, maybe for one context, and now you're applying them to a different data set with different circumstances in theory. You can't really be sure the software is working as intended, even if it gives you a number rather than an error message. So one of the things McElreath emphasizes is that a lot of the software that is most commonly used can be very brittle. And it yields an answer that isn't really good if you're using it in a way that it wasn't intended to. But that's sort of often the case in science. We're trying to learn as we go. But when applying it to new areas, the software doesn't always work nearly as well as you might hope. And then fifth sort of uncertainty as to whether the model is going to continue to hold with other data, maybe future data. Or could something about the data generating process change between now and then? And the possibility of that should make you more uncertain about the future than your model says you should be, based on the past data. And as I was sort of, defining Bayesian inference, at least in high level, we use probability to describe the uncertainty in 1 and 2 and 5. which along with something that's very closely related to Bayesian, but it's a little bit different, known as decision theory, which prescribes three to sort of give us a way to make decisions, to make actions that propagate all the uncertainty through and phrase it in terms of probabilities of events. So 4, like I said, is a little bit different. With the STAN software, we're doing as much as we can to mitigate that. But it can't be done perfectly. What is good about STAN and what makes it distinct from a lot of other software is STAN can tell you if it thinks it's having problems. It just doesn't, just give you a number or whatever output the way a lot of software does, because a lot of software, it makes its assumptions and whatever, but it can't really tell you something is wrong from its own output, because its own output is generated under the assumption that nothing is wrong, things are working well. With STAN, there's actually a variety of ways in which it can give you warnings like, hey, I don't think this is what it's supposed to be looking like, and so that is actually a good thing, even though it can be frustrating when that happens. And other forms of inference besides Bayesian inference are going to make different choices, different trade-offs in terms of how they deal with these things. So example of Bayesian inference, loosely speaking. So what do you all believe is the average age among Columbia graduate students?
25.
25? Okay. So could you describe obviously you're not completely sure that it's exactly 25, but could you describe your beliefs about what the average age of a Columbia graduate student is using a normal distribution, maybe which has its center at 25, or you could use a different center. But the normal distribution also has another parameter, the standard deviation or the variance, that gives it that bell shape. So you could say your uncertainty is, okay, with the normal distribution, like 2/3 of it is within plus or minus 1 standard deviation of the center. Let's say the center is 25. So in order to complete this normal distribution, what would you say is like the standard deviation for what you think the average age is of a Columbia graduate student? So, there's a 2/3 chance that the average is between plus or minus what of 25?
3,
Something like that? 2
2.
1.5.
can be any positive real number. So all those are fine. All those are admissible. Okay. So we've described our beliefs using a normal distribution, and the Bayesian approach is going to transform this initial normal distribution into another distribution. If you observe a bunch of data, like the ages among a bunch of actual Columbia graduates. So imagine you all are a sample. If we took your ages and we started with that 25-2 or whatever normal distribution, okay, I get my 25-2 normal distribution, I get data from the 40 whatever of you, combine that together, I get out a new probability distribution to describe my updated beliefs about the ages of graduate students at Columbia. So that is a high level is what Bayesian inference does. You start with an initial probability distribution, so you've got to be able to describe what you believe in terms of a probability distribution. It doesn't have to be normal, but normal might be the one that you're most familiar with, so that's fine for today. So start with some initial probability distribution, add data, combine those together, come out with a new probability distribution that represents your updated beliefs about whatever it is we're talking about. Okay? But that process is quite different from other forms of quantitative method inference, in particular randomization inference, which is also known as design-based inference, frequentist inference, supervised learning, other things that yield point or interval estimates, as opposed to the Bayesian approach, where the output of it is a probability distribution, rather than a point or an interval or anything else. It's a distribution. And so that, these different other forms of inferences you can see is contrasting with that. So here's an example of randomization inference. So if you have a coin, you can just flip a coin, or if you want to open up R or something like that, form a pair with your neighbor, and then exactly one person in each pair should randomize. So now you can take a sample from me and you of size 1 and R, or just flip a coin for heads or tails or whatever, or do like odds and evens, do some sort of randomization process to define who is me and who is you, and then compute the difference in age between the indicated person, let's call that person getting the treatment, and the other person in the pair, let's call that the control person. And so compute their difference in age between the treated person and the control person, which of course can be negative if the control person is older than the treated person. All right, so do that with your neighbor or whatever, form pairs, come up with that number, randomize who's treated, who's control. Randomly designate or just arbitrarily designate someone is treated, someone is control. What is the difference in age in the pair between treated person and control person? Okay, so we're learning something about your neighbors. That's all. But abstractly, so what do you think is the average of these differences between the age of the treated person and the control person in this class? If you randomize who is treated and who's control? 0. We would expect the difference to be 0. But the difference is not going to be 0 every single time. Particularly like if you just did it in terms of age, number of birthday parties that you've had, like that's fine. But if we did it in terms of like years and months, how old you are, then it's almost never going to be exactly 0. So how much do you think the average in this class of the pair differences could depart from 0? All right. So maybe we could estimate the variance in the difference between the treated person and the control person. So this is an example, and if we did it, with different ways of pairing, we would get a slightly different answer. All right, and there are whatever number this is, that many ways to form pairs among 42 students, which is the number of people who were registered for this last time I checked. And so rather than enumerating all, however big a number this is, of different differences, and remember this was created about 100 years ago by Fisher, which it would have been impossible to enumerate anything bigger than like a few thousand. So instead of enumerating all those things, we use a probability distribution to describe the differences in the pairs. And that distribution is going to have a center at 0, but it's not going to be exactly 0. It could be a little bit positive. It could be a little bit negative. How positive and how negative it could be might be described with a distribution like this. This is the standard normal distribution, and this is where p-values originally come from. Fisher would say, okay, do an experiment where you pair observations based on their similarity on background variables. He wasn't really talking about people, he was talking about plants primarily. but that one randomly gets to be treated, one randomly gets to be controlled. The treated plant maybe gets a different fertilizer or whatever, and then you see how big the plant, the difference in how big the plant grows, subtract one from the other. If the fertilizer has no effect relative to the previous fertilizer, then you would expect the difference in the plant output to be about 0. But if you observe an average difference between the treated and controlled groups, that, you know, once you standardize by the standard deviation, it's greater than 2, well, you could say there's only like a 2.5% chance of observing a difference in the average that's this big if in fact the new fertilizer has no different effect than the old fertilizer. So that's an example at a sort of high level of how Fisher was thinking about randomization inference, but it's limited certainly to the case where you can randomize who is treatment or what is treatment and what is control. By itself, it's not particularly suitable for observational studies, and we have both in the social sciences, obviously. But, you know, p-values are associated with this idea, well, you know, if the observed estimate is out over here, rejecting the null hypothesis that the treatment has no effect. And that way of thinking has sort of carried over to one of Fisher's other contributions, which was frequentism. And even another one which is called fiducial inference, which you probably have not heard of because it fortunately died out. But anyway, the reading for today, particularly McElreath, makes I think, an important statement where he says the greatest obstacle that I, McElreath, but I, Ben, agree with him, encounter among students and colleagues, his students and colleagues are like evolutionary biologist type people, is the tacit belief that the proper objective of statistical inference is to test null hypotheses. And this comes from kind of a distorted philosophy of science of Karl Popper, which, you know, sort of says, well, we proceed by, you know, rejecting hypotheses and whatnot. And the reason why McElreath says that this is like an obstacle, this is wrong, is that hypotheses are not synonymous with models. So a model will usually entail multiple hypotheses or assumptions or whatever that goes into it. So let's say a model consists of multiple hypotheses. And let's say we find that the model doesn't really fit the data to some extent. Well, that on its own doesn't tell us which of the assumptions or hypotheses that we made were wrong, because the model kind of glued together a number of assumptions or theories, any one of which or all of which could be wrong to some extent, and that could explain why the data that we observe deviate from the model to some extent. But again, the Bayesian approach, rather than saying, okay, this data is consistent with the model or this data is not consistent with the model, is going to get into the shades of gray. How inconsistent is this data with the model? What's the probability of observing you know, a data set that would be more inconsistent? Things like that. Also, there's no conclusive way of saying what's the null model, like what's the default model that you should start with against which other models should be compared. A lot of the debates in the social science literature are about like what should be the default model, but there's no logical reason why one or the other should take precedence over another, and that's one of the limitations of the frequentist approach to things, where the null hypothesis is one that you have to have like a sufficient amount of evidence against in order to reject, but like who gets to be the null model? Like that seems to be like a privileged sort of deal. Whereas the Bayesian approach can say, okay, kind of, we have some candidate models and they're all on equal footing to start with, and then we're gonna update our beliefs about them with data, and we can see like that. So the lack of a one-to-one correspondence between hypotheses and models makes this falsification thing not great for social sciences, including the sort of extended social sciences that McElreath is interested in, having to do with like evolution of societies and stuff like that. Also, oh, did you have a question or comment? No. Also, measurement error. So there's a ton of that in the social sciences, prevents you from basically being able to say this is absolutely false. So let's say we have, a model, a collection of models or whatever. We observe some data. The data are not perfectly consistent with any of those models, but it might be the data's fault, or whoever measured the data. It might be their fault, even if there's not a whole lot they could do about it. The data might be mismeasured or missing. That's kind of an extreme form of it. And so the inconsistencies that we observe between the data and the model, maybe the true data would have looked more consistent with the model, but the observed data with the measurement error embedded in it looks, worse. But we shouldn't really be like absolutely rejecting a model just because it's not perfectly aligned with data that we know is imprecise at best in how we measure it. And that's just kind of another fact of life of social sciences. We can't even really define all our concepts absolutely precisely, much less measure them the way the concepts dictate. And so those are McElreath's main two reasons why he doesn't think this deductive approach is good for social science. We need an inductive approach, which the Bayesian thing is more aligned with. Moreover, also it goes on to talk about, which I also agree with, science should be hinging upon what a treatment effect or other estimate is, rather than what it's not. So if we go back to like randomization inference, we might say, okay, this treatment effect of the fertilizer is not 0. Well, that's an almost vacuous statement. That is insufficient for like the farmer to decide, do you want to use the new fertilizer or keep using the old fertilizer, if all it is I tell you is the difference between them is not 0. Like, how are you supposed to decide whether you use the new fertilizer or not? Even if I say, well, the new fertilizer is estimated to be 3% better. Well, what if it costs like $100 more? How would you make the decision as to whether you should use this better, estimated to be better, but we don't even know if our estimate is right, fertilizer, if we know I have to pay a lot more money for the new fertilizer? Sort of thing. But so in order to make that decision, you have to get at to what the treatment effect is, not what it isn't, which is the null value. So Bayesian doesn't do that. Also, McElreath, among other people, gets into the crisis in psychology business. Science requires honesty and transparency about our uncertainty in what we know, even after we've observed the data. So it from the farmer's perspective, it doesn't do a whole lot of good to say we've estimated it, the new fertilizer, to be 3% better than the old fertilizer. Well, how sure are you in that 3%? That's another ingredient that needs to go if we want to proceed in a reasonable fashion. So frequentist inference might ask ourselves, what's the average age among Columbia graduate students? Same question. So let's say each row of this, whatever you call it, curvy row thing, is a sample from that population. We could sum up all the ages from left to right in a row. And the rightmost person could divide, and we would get estimate of the average age of Columbia graduate students. They wouldn't be exactly the same. Each row would get a slightly different number out at the end. But the central limit theorem, which is almost synonymous with frequentist inference, almost everything in frequentist inference involves some variation on the central limit theorem, somehow says the distribution of average ages among groups or whatever is asymptotically distributed normal, with the center of that normal distribution being the true population average age of Columbia graduate students. So we could get like 4 or 5 different estimates if each row is a sample, and the central limit theorem assures us for large N, which we might be a little bit too small to be large N, but if we had larger N, the distribution of averages is normal, and the center of that distribution is the true population average. But we don't know what the true population average is, nor do we know what the true standard deviation of the population is, so the standard deviation of ages in our population. And that can't be known with certainty from any finite amount of data. So you will see a lot with this frequentist stuff saying, okay, well, what if n goes to infinity? And make a whole lot of conclusions about the estimator under the assumption that n is infinite. But in the real world, data is finite. And so we can't know for certain how well those asymptotic approximations or arguments are going to be when applying them to finite amounts of data. But like I was saying, frequentist inference sort of inherited a lot of this deduction, and like things are true or false, and we just need to figure out which way of looking at things, as opposed to saying, you know, degree of belief about whether something is true. And so frequentist inference often proceeds, you know, something a lot like this. If the null hypothesis is true, then the standardized estimator will be greater than 1.96 in magnitude in 5% of possible samples of size n. So it's kind of like a major premise. Kind of minor premise, well, the p-value that I observe from this particular sample is less than 0.05. Ergo 3, the null hypothesis of no difference or whatever is falsified. So you can see how this resembles in structure the Aristotle thing. But it's not as absolute to it. So, you know, major premise involves like a 5% probability, as opposed to saying something like, you know, 95% of humans are animals, or something like that, which Aristotle didn't say. So it kind of has the Aristotle structure of it, but you have these like small probability exceptions to it, in which case 3 doesn't even really absolutely follow from 1 or 2, even if 1 or 2 are correct, because like there's a 5% type 1 error rate. This estimate could be messed up for any number of reasons or whatever. So it could be the case the null hypothesis is true, even though the procedure says it's falsified. But then we have to ask ourselves the question, what scientific or substantive purpose would really be accomplished by declaring the null hypothesis to be not literally true? So it could be approximately true, but false. It could be, you know, false by so little that the difference is negligible. So like the good fertilizer is like a tiny bit better than the old fertilizer. That's maybe true, but it costs so much more that the farmer wouldn't want to buy the new fertilizer. So the difference may be negligible compared to the cost. But anyway, all of that is not really answered by the frequentist framework, or indeed any framework that looks at everything, it's true or false. And we gotta choose which. Rather than allowing sort of like degrees of belief as to whether something is true. And then last few minutes here, let's talk a little bit about supervised learning, which you may be more familiar with some of your fall classes. And an example of something like in the picture that we started off in the first slide with, if I put the number of articles in the social sciences that use supervised learning over that past period, it would be like none, 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 and then pretty steadily increasing in the past decade or two. So it's not the case that social science can't change as new technology gets introduced, but they have changed in response to supervised learning technology, neural nets, large language models, text classification, all these sorts of things. So that has happened, but for the most part, the use of Bayesian inference pretty much has not increased very much. But anyway, so supervised learning, it's like frequentist estimation, but without the null hypothesis stuff. You estimate the parameters. So there's a usual convention in supervised learning to distinguish between testing and training. So let's say the first 3 rows here are training data, and the back row there is testing data. So if we want to take a supervised learning approach to estimating the age, we would take our 3 rows of training data, estimate the average age among them, and then we would use that estimate, let's say 25.6 or something like that, and then take it to the back row and see how much the back row, the testing data, deviates from the prediction that we ascertained from the training data. So there's no like testing a null hypothesis that the average age in Columbia grad students is 25.3 or whatever, which we may or may not be able to reject or whatever. Just skip all that. Estimate, use the model to form predictions, apply the predictions in the testing data, and evaluate how well you can predict in the testing data based on your model that was applied to the training data. So often the testing data is going to be a random subset of the total data, but supervised learning typically does not consider the probability implications of that randomization. So when we were thinking about randomization and inference, we were like, well, there's 5 blah, 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 like quadrillion ways in which we could make all these pairs. Well, there's a similarly mind-bogglingly huge number of ways that we could chop a data set up into like 80% training and 20% testing. And depending on how you do the chopping, you're going to get slightly different answers, slightly different predictions. And you might think, well, we should use a probability distribution to describe how much the estimator differs depending on who gets to be in training and who's in testing. But supervised learning doesn't often do that. Indeed, they don't really emphasize probability that much at all because it's another big obstacle to learn. And they want people to get into doing these things for as wide a subset of people as they can. But also the supervised learning stuff, which tends to come more from engineering and from computer science than from statistics or social sciences, is often intended to be used with enormous amounts of data. Whereas a lot of times in the social sciences, our data sets, even if they're big, are orders of magnitude less than what the people who develop these neural nets and whatnot are having in mind when they're thinking about the applicability of their stuff. Also, you know, supervised learning has a fairly well-deserved reputation for being fairly atheoretical. Like you just kind of throw the stock prices of everything in the S&P 500 into the like convoluted neural net, and it like convolutes itself more, and you get out these predictions as to what the stock prices are going to be tomorrow, and then you like make your investments today on the basis of that or whatever. without having any opportunity to put in any sort of theory or other sorts of things, which the Bayesian sort of does. So we're out of time, but I just want to leave you with this table, and we'll come back to a lot of these ideas over the course of the semester, sort of laying out these 4-ish different quantitative methods for analyzing stuff, in particular in the social sciences, and seeing, on these different questions that are in the columns, how the different methods in particular contrast with the Bayesian method and, the answer that we get in these stuff. So anyway, hope to see you all same time, same place next week. Even if you're still on the wait list, continue to come. We have plenty of chairs, so I'm sure you'll have a spot in the class eventually. And watch your email. We're going to have a recitation session at some point before next Thursday. It'll be over Zoom, but we want to get everybody's laptop installed with all the software that you're going to. Question? Good. No, I won't. I'll stay on next class, but. If anybody.
Yeah, like